Hi, welcome to this fifth video in the lecture series of Bayesian statistics. Of course, actually what we're doing is machine learning. And in this video, we will look at a new topic, and that is the topic of classification. What we have done so far is that we have only been looking at situations in which the outcome variable was continuous. That is usually in machine learning called regression. I don't like that word too much because of the fact that you should realize that at the moment that we have an outcome variable which is continuous, then we typically do much more than just regression. On the other hand, as we will see, that at the moment that we have a discrete outcome variable, then we actually also do regression. So therefore, I prefer usually to say that the outcome variable is continuous. But today what we're going to do is that we're going to look at the discrete outcome case. Well, that is usually called classification in machine learning. And honestly speaking, I like that word actually quite a lot because of the fact that that's exactly what you do. And it's different from what we typically do in econometrics. In order to start with classification, classification implies that the outcome variable y takes one of c different outcomes. We typically call them classes, and the c that we have over here is going to be finite. That means, well, purely mathematically said, or probability theory said, that we are going to restrict ourselves a little bit more than just a discrete outcome variable, because of the fact that apart from the fact that we have a discrete outcome variable, the number of outcomes is also going to be finite, because we're going to assume that this c that we have over here is in fact finite. That's a little bit more restrictive because of the fact that, discrete outcome variables could still take infinitely many different outcomes, but that's here not the case. Well, the simplest is to think of the case in which the supporter y can take the outcomes equal to 0, 1, up till c minus 1. This might look a little bit too difficult because of the fact that what we could have done as well is to start here with 1 and then end up here with c. But I'm not going to do that. And the reason behind that is because of the fact that this is actually a very nice generalization of the case in which we have c equal to 2. If we would have had c equal to 2, so just two different classes, well, then in that particular situation, we would have the case in which this outcome variable was generally being called a dummy variable. Then we would have had a dummy variable, then the outcomes would have been equal to 0 and 1. Well, that means, of course, that is exactly the same what we have over here, because of the fact that if I substitute in here c equal to 2, well, then actually 1 is also going to be our last number. So therefore, we are going to use this notation over here and take into account that this is also the way in which Python looks at this, because Python always starts to count with 0 up till, say, c minus 1. And lots of people actually don't like that, but we could at least say that that is exactly the way in which also computer programs like Python actually try to count. Now we can come back to the supervised learning problem. Remember that generally the supervised learning problem is to predict our outcome variable. In this case, in the case of classification, the supervised learning problem is now to predict the class for a particular realization of x equal to this little x over here. So that means again that what we're going to have is that our predictor g hat x, well, it's maybe better to say the estimator of our predictor in this case, will only take outcomes, well, that are also going to be equal to 0, 1, up till c minus 1. Exactly the outcomes that we had over there. Well, even though that sounds, well, very obvious that you actually should do that, you should realize that we as econometricians typically don't actually do that at the moment that we are going to think about predictions. At the moment that we are going to, for example, run a linear probability model, then we can make predictions, of course. We typically do that. Well, in Stata, you can actually do that by predict. And then what we're going to get is that even though we assume, of course, that the outcome variable is a dummy variable, and we're only going to have outcomes equal to 0 and 1, at the moment that we as econometricians, not as machine learners, are going to make predictions, then what we typically predict in a linear probability model is not whether we have a 0 or 1, but we are going to predict the probabilities. So a typical prediction then in a linear probability model is 80% or 95% or something like that. We're not going to say that the prediction is going to be equal to 0 or equal to 1. And we do exactly the same at the moment that we're going to look at a logit or a probit model. Well, we should realize that that doesn't make that much sense at the moment that we're going to look at machine learning. And that's immediately clear at the moment that we're going to look at our examples. Remember, for example, that example that we had with respect to Facebook, where Facebook is going to have an algorithm to see whether there is a face in a particular picture or not. Well, in this particular case, it doesn't make that much sense that, say, Facebook is going to tell you at the moment that you have been uploading a picture that there is a 95% probability that there is a face in that particular picture. First of all, you should realize that most of the users of Facebook have no idea what actually a probability is. And in addition to that, well, it doesn't even make that much sense, even at the moment that you know what a probability is, that you're going to get a 95% chance or probability that there is a face in a particular picture, because we as human beings can immediately see whether there's a face in a picture or not. So therefore, it's not that much information to know whether there is a face in the picture or not, or whether that's with a particular probability. So therefore, what we typically do is that even though we might then sometimes be wrong, of course, it may be possible that we are going to predict a face in a picture, but there is actually no face over there. We just are going to make a prediction equal to 0 or 1 in this case. You can also look at other examples, such as, for example, the credit worthiness of customers for a loan or a credit card. Well, the most interesting thing is, of course, to think of a situation in which you're going to buy a house. So typically people don't have cash to buy a house, they need a mortgage for that. And then what you typically do, or at least what we did before Corona started, was that you're going to have a meeting with somebody at a bank, somebody who's definitely paid much too much, and that person is going to talk to you. Well, first of all, you're going to get a cup of coffee from that person, and then after that, he's going to talk to you about many, many things, of course, but including how high your income is, well, and well, other things like what kind of position do you have in your job, what kind of job you have, and also especially whether you have a permanent position or just a, well, timely position. Well, based on all that information, well, maybe you even have to meet that person another time, but based on that, at the particular moment in time, the, well, person is going to tell you whether you're going to get a mortgage or not, and of course how much you can actually get as a loan, and maybe he or she is even going to tell you something about the interest rate. Well, this you could of course do by somebody who's having a very high salary, but computers can do exactly the same. What we could do is, of course, just, well, enter the information about a particular customer into the computer, and it would be so nice if the computer can immediately say whether, well, that computer, based of course on an algorithm and based on the information that you have, whether it's a good idea to give that particular person a mortgage or not. Well, unfortunately, we're not that far yet. I'm pretty sure that even after Corona, well, we are going to still have to go to banks, but you should realize that with other cases, well, banks already use it. For example, at the moment that you are going to get a credit card or you're going to apply for a credit card, you can now these days do that online. And at least the good banks, well, they are going to use machine learning to see whether somebody is credit worthy or not. You're going to enter information about you, again, your income and things like that. But also banks usually already have a lot of information about you. Well, whether you have had a credit card in the past, whether you have been paying that credit card in the past, and how many credit cards you have right now. So all that information we can use in order to see whether a particular customer is credit worthy or not. You can also think of this interesting, say, example that we have over here. It's very interesting, very classical actually, but maybe nowadays it's getting less and less important. And that's the recognition of handwritten digits. An application with respect to that is at the moment that you have to find out which letters and postcards, well, old-fashioned letters and postcards, have to go to which, say, city in the Netherlands. In the Netherlands, we have this nice system of zip codes. And in the old days, of course, say 20 years ago at least, well, then there was somebody who was going to read all the different zip codes. And based on these zip codes, you can see where, say, particular postcards and letters have to go to. Well, you should realize that that takes a lot of time. Computers can do that as well. They can make pictures, and based on their pictures, they can use machine learning in order to find out what kind of digits we have. Do we have a 3 or a 7 or a 9? Well, and then finally, we can also think of the example that I have already talked about before, heart attack screening. Well, now let's look a little bit more at the theory. Remember that the loss function that we use for classification is this loss function that we've over here. So we do already know that loss function always depends on two things: our outcome, or the realization of our outcome, and our prediction that we have made. And the loss function in this case is going to be equal to 1 in the case that we make a wrong, say, classification, if we make an error. So in the case that y and y hat are not equal to each other. Then in that particular moment in time, we're going to get a 1. In the case that we make the correct prediction, then of course we don't have a loss. And then at that moment in time, this thing that we have here at the right hand side is going to be equal to 0. Well, this is something that we already know. And another thing that we have already seen before is that in the continuous case, so not in the classification case, but in the continuous case, we did not use this loss function that we have over here, but we used the quadratic loss function. And remember that then after introducing the quadratic loss function, I said that there was something very nice with respect to quadratic loss function in the continuous case. And that is that then the unknown, say, best predictor, that we always labeled by G star X, that then is always going to be equal to the mean of y conditional on x equal to x. And I said that that is really, really important because of the fact that then, well, all the estimation methods are in fact based on that. Even though we do not know what the mean of y conditional x equal to x is, we can try to estimate that. And that is in fact all the estimation methods that we have seen so far actually do that exactly. Regression does that. So lasso and ridge regression try to do that, but also local linear regression, kernel regression, as well as nearest neighbors. All these kind of methods actually have only one goal, and that is to estimate the mean of y conditional x. Well, we do of course know that that doesn't hold for the classification problem. For the classification problem, we cannot look at the mean of y conditional on x, but fortunately there is something else. You can actually show that at the moment that you're going to use this loss function, and at the moment that you of course would like to minimize the theoretical risk, then, well, G star X is always going to look like this thing that we have over here. It's going to be the argument that is going to maximize these probabilities that we have over here with respect to all the classes. So what that means is that in this case, G star X is always going to be a number in between 0 and c minus 1, as we already have seen at the previous slide. So it's not, it cannot be equal to 1.5 or something like that, or pi, as you can have in the continuous case, but it's always an outcome which is equal to 0, 1, up till c minus 1. And G star X, based of course on a particular value of X that we have over here, is always going to be, well, that value of this Y that we have over here, for which this probability is going to be higher. Well, again, this is of course very valuable because of the fact that even though we don't know these probabilities that we have over here, we can try to estimate them. And if we are able to estimate these probabilities that we have over here, then the only thing that we have to do in a classification problem is choose that particular class that has the highest estimated probability. Well, we'll see later on that all the, say, classification methods that we're going to look at have this idea, that we are going to choose that class that has the highest estimated probability. But before we're going to do that, we still have to prove this thing that we've over here. Well, so therefore here we have to prove. What I'm going to do And the proof is, of course, a lot in line with what we have done also in the continuous case. And remember that in the continuous case, the first thing that I did was to define a function hx, and hx is simply equal to the right-hand side of what we have over here. So this thing that we've over here. But before I go further, it is nice to realize that this is really a function of x. And the reason behind that is, first of all, because of the fact that this is not a function of, for example, this y that we have over here, because of the fact that we maximize with respect to y. So therefore, the ultimate product that we are going to have here at the right-hand side doesn't depend on y. It's just a particular number, but it doesn't depend on y itself. Of course, it also doesn't depend on this large y and that large x that we have over here, because of the fact that these are stochastic variables. However, this thing that we have here at the right-hand side does depend on this little x that we have over here. And that makes, of course, sense, because of the fact that we can expect that these probabilities that we have over here depend on this x that we have over there. Well, otherwise, this x over here would not be any good predictor at all if it doesn't say anything about these probabilities that we have over here. So therefore, we can expect that there is a well, at least x and y are going to be dependent upon each other. And that means, of course, that at the moment that I'm going to change the value of x over here, well, then this function that we have over here is also going to change. So therefore, this is really a function of this little x that we have over here. Well, now let's go on with the proof. Well, the main question that arises right now is, of course, what do we have to prove? Well, that's a thing that we actually already know from the previous proof that we have made with respect to the continuous case. The only thing that we actually have to prove is that for any function g that we have over here, the theoretical risk should be large or equal to the theoretical risk evaluated in this h that we have over here. So that means that the only thing that we actually have to have in the end is that this LG is going to be larger or equal to L evaluated in H. So that's the only thing that I actually would like to get in the end. Then I'm satisfied. Well, we do already know what this risk function is, this theoretical risk is, because of the fact that that is by definition, of course, equal to this mean that we have over here. Generally, the theoretical risk is equal to the mean of loss function, but in this case, we have this loss function over here. So therefore, we're going to get this theoretical risk that we have over here. Well, now we can rewrite this a little bit. The first thing that we can do is that we can, well, condition here on the different values of this x that we have over there. So therefore, we're going to get an integral. We're going to get an integral over x. We get exactly the same mean as what we had before, but now conditional on x equal to little x. And we multiply this now by either the density or the probability function of x, depending, of course, on whether x is a continuously or discretely distributed random variable. So this is the first step that we're going to have. Then we should realize that this x that we have over here is equal to that x that we have over there. That one is equal to little x. So also this thing that we have over here is equal to little x. And then the next thing that we can do is that we can now realize that this is a mean with respect to y. And y is discretely distributed. So in this case, we do already know that even though we can write this as an integral, we can also write this as the sum of the outcomes multiplied by the probabilities. The outcomes in this case are, of course, not y itself, but they're equal to this, say, function that we have over here. So therefore, what we can do is that we can now sum over all the potential outcomes of y. That's, of course, from 0 to c minus 1. We're going to get here that function that we already had, but now little y instead of large y, and multiplied by the probabilities of the y that we have over there. Well, then the next step that we can take into account is that even though we are going to sum here over all the potential outcomes, we do, of course, know that this indicator function that we have over here is only going to be equal to 1 in the case that y is unequal to gx. So instead of, say, summing over all the y's that we have over here, we can also sum only over those y's for which we do know that this y is unequal to gx. So we can also write it like this. And now what we actually do is that we sum now over all the probabilities for which y is unequal to gx. That's, of course, nothing else as simply the probability that y is unequal to gx. That is very simple. At the moment that I'm going to throw a dice, and I would like to know what is the probability that I'm not going to throw 5, well, that's of course equal to the probability or the sum of the probabilities of 1, 2, 3, 4, and 6. So therefore, we should realize that this whole thing is nothing else as the probability that y is unequal to gx. So this thing that we've got now over here. Well, then the next thing that we can now do is that we can now realize that the probability y equal to gx is of course nothing else as 1 minus probability that y is equal to gx. And then the next thing I can do is that I can take this one out of the integral. So therefore we get this thing that we've over here. Well, this was still all quite straightforward, but now we get the most important step. Now we should realize that by this definition that we have over here, that hx is going to be the argument that is going to maximize this probability over here. That means, of course, that, well, whatever this probability is going to be, it will never be larger than the probability of y exactly equal to hx for this x that we have over there. So including, of course, this gx that we have over here. So that means that whatever this gx is going to be, well, this probability that we have here in the integral is smaller or equal to this probability that we have over there. Well, that means, of course, that, well, if we are going to look at the whole integral, this holds not just for just one x, but it holds for all the x's in the support of this large x that we have over there. So that means that this whole integral is going to become, say, larger at the moment that I'm going to replace this g by this h that we have over there. That's the thing that we should realize, that if I'm going to not write this as in terms of gx, but now in terms of hx, then this integral should actually become larger. And the reason behind that is because of the fact that by definition, this probability over here is smaller than the probability that we would have had over there. Well, now we have a minus sign in front. So there we should realize that if I replace gx by hx, given the minus sign, this part over here is going to be smaller. And that means, of course, that we can now realize that at the moment that I'm going to replace this with respect to hx, then this whole thing is going to become smaller. And that means, of course, that the theoretical risk in this g that we have over here is going to be larger or equal to this thing that we have now at the right hand side with just g replaced by h. Well, and now we should realize that we are now almost done, because of the fact that what only thing that I now have to do is to show that this thing that we have here at the right hand side is the theoretical risk evaluated in h. Well, that's actually not that difficult, because you should realize that what we have done so far up to the previous step is doing nothing else as trying to rewrite this function that we have over here in terms of this thing over here. And now we have almost the same thing, but now we have, say, not g, but we have h. So the question arises, how do I get now the theoretical risk in terms of h? Well, that's pretty simple. I just have to do all the steps that I have done so far, but the other way around. So first of all, I'm going to bring the 1 here into the integral. So then we get this thing over here. Then I should realize that this is, of course, nothing else as the probability that y is unequal to hx. Well, then what I can do is that I can here sum over all the outcomes for which y is unequal to hx with respect to the probabilities, as I do over here. Then I can realize that, of course, I can only say sum over all those probabilities for which y is unequal to hx, but I can also sum over all the potential outcomes, but then I need this indicator function that we have over here, which is going to indicate that y should be unequal to hx. And then we should realize that this is now going to be the mean of, say, this thing that we have over here, that the indicator function that we had before, because of the fact that we sum here over the potential outcomes multiplied by the probabilities. So, and then we should realize that, of course, this can simply be written as the mean of, well, this indicator function, not conditional on this x that we have over here. So therefore, we now have this thing over here. And now we're in fact done because of the fact that this is exactly equal to the theoretical risk evaluated in the function h. So now we actually have proven the thing that I wanted to prove. Well, this is actually true. Well, at the moment that we would like to have the best predictor, well, the best predictor will always have this thing that we have over here. I already said that this is really nice because of the fact that that means that if we would have known these probabilities over here, well, then the only thing that we need to do is, in fact, to choose that particular class for which this probability is going to be largest, given a particular value of x. Well, we can say it in that way, but we can also define it a little bit differently. What we can do is that we can look at so-called decision spaces. Decision spaces are nothing else as, say, subspaces or subsets with respect to the total support of x, and they are going to be all those x's in effect for which we are going to choose a particular class. So we have here these decision spaces x0, x1 up till xc minus 1. And more in particular, if we, for example, are going to look at this x1 that we have over here, then at the moment that our realization of x, this little x that we have over here, is going to be a, say, element of x1, well, then we simply know that the highest probability is with respect to, say, the first class, when y is equal to 1. So then we simply are going to predict y as being equal to 1. So more in general, we are going to have this thing that we have over here. Well, you should realize that these decision spaces that we have over here are, so to say, disjoint. And the reason behind that is, of course, because of the fact that they're by definition equal to those areas in which one of these classes is going to have strictly the highest, say, probability. So for example, if we're going to look at this class over here, well, that is the class of x's for which, say, y equal to 1, conditional x equal to x, is strictly going to be highest. Well, then it's impossible, of course, that any of the other classes also is going to have a probability that's going to be strictly highest. That is impossible because of the fact that then the class 1 would not have been strictly highest. So that means, of course, that these sets are going to be completely disjoint. However, it is, of course, possible that we are going to have a combination of the x's, so that we are going to have an outcome of the x's in which it is possible that two, say, classes have exactly the same probability and they are going to be highest. Well, in that case, we are going to be, well, indifferent between which class we are going to choose. Well, generally, if this thing is going to be continuous, the likelihood that that's going to happen is not that high, of course, but we should realize that then we are going to be in the so-called decision boundary. So the decision boundaries are nothing else as those combinations of the x's where we have two classes which are going to be having exactly the same probability. More in particular, we could look at the decision boundary of class I that we have over here, where in fact the probability of class I conditional x equal to x is the highest, but there is at least one other class that is also has exactly the same probability. These are these boundaries that we have over here, and we should realize that delta Ix is sometimes also called a discriminant function. I like more the decision boundary because of the fact that I have the idea, well, then I can understand that we have this kind of boundaries. It's also not really a function, it's more like a p-dimensional map. Well, this is all quite theoretical, maybe not that clear right now, so therefore it is good to look at an example. Suppose, for example, that c is equal to 2, so we only have two outcomes. Y can be equal to 0, and y could be equal to 1. Let's now look at the, say, decision space x1. Well, then that particular decision space is determined as follows. It's all those combinations of x in the total support of this x that we have over here, for which the probability that y is equal to 1, conditional x equal to x, is larger than the probability y equal to 0, conditional x equal to x. Well, we do, of course, know that the probability in this case of y equal to 0 is nothing else as 1 minus the probability that y is equal to 1, because we only have two potential outcomes. I can now bring this probability to the other side in order to realize that if we now divide the left and the right hand side here by 2, that means actually nothing else is that we need to have a probability that for y is equal to 1, conditional x equal to x, which is larger than half. Well, that makes, of course, sense. At the moment that we're going to have only two outcomes, for example, in the Facebook example, we have either a face or not. Well, then at the moment that we are going to predict the situation in which the situation of a face is larger than 50%, maybe for example 95 or 99%, well then in that particular situation, it would be better to predict that there is a face in that particular picture. And at the moment that the probability of having a face is smaller than a half, well then actually it's better to, in a sense, predict that there is no, say, face in that particular picture. So that is, in a sense, the idea behind this. Well, at the moment that we're going to look at the decision boundary, well, in the case that C is equal to 2, well, then it doesn't make that much sense to write down the decision boundary for 1 and also 1 for 0, because of the fact that they're exactly identical to each other. Well, the decision boundary is in this case, of course, nothing else as all those combinations of the x's for which the probabilities are exactly identical to each other. Well, that means in our case, of course, all those combinations for which the probabilities are exactly equal to a half. So this is the case that in which we have C equal to 2. Well, more in the general case, we're going to have many more, say, of these spaces. And you should realize that, for example, if you're going to go back to the situation in which we are going to make a decision with respect to digits, so handwritten digits, at the moment that we're going to see that, for example, the probability of having a 4 is going to be highest, and it's higher than any other probability, given, of course, all kinds of characteristics that we know about that particular case, most likely, say, the pixels of a particular picture again. Well, then, based on that, at the moment that we see the probability of 4 is going to be highest, then we simply are going to predict 4, and of course not 7, for example. Many methods assume that the decision boundary delta ix is linear. Well, I will discuss a couple of these different methods, and the methods I'm going to discuss are linear regression methods, linear discriminant analysis, usually called LDA, but we have also a nonlinear extension of LDA, and that is usually called quadratic discriminant analysis, or QDA. And finally, we're going to look at logistic regression. We should realize that even though these methods by themselves are linear, that is to say that they're linear in, say, the final axis that we're going to use, that doesn't mean that they always have to be linear in, say, the original features that we're going to use. In that sense, we should realize that we have already looked at series regression. What is series regression? Well, you could say that series regression is nothing else as, say, standard ordinary squares linear regression. However, we allow for non-linear relationships. Well, in the end, we even allow for, say, non-parametric relationships in series regression by including higher order terms. Well, that we can do here as well, of course, even though, for example, this linear regression method that we're going to look at later on is, of course, linear in the final axis as series regression, but we can, of course, always include higher order terms. But that, of course, still makes these methods, in a sense, linear, and they're not really non-linear methods. And that's the same as in regression analysis. You should realize that there are really non-linear methods in regression analysis, such as, for example, NLS, non-linear least squares. Well, that we will see here as well. There are actually real non-linear methods as well in classification. Well, one of them we have already looked at, QDA, but you should realize that also nearest neighbors is going to be a non-linear method in classification. Well, that's a method that we have already seen before, but we will have to adapt it a little bit. And also trees that we're going to look at later on are going to be non-linear methods. Also, neural networks are non-linear methods, but we are not going to look too much at these neural networks during this lecture series. Well, what I'm going to do is I'm going to discuss all these different methods, but before I'm going to do that, I have to actually look at an intermezzo. What I finally would like to do is that I would like to look at a computer simulation, but for the computer simulation, I need so-called mixture distributions or mixture models. And I'm not exactly sure whether you have ever had that before, but in order to not run the risk that in the end, well, nobody is going to understand this, I'm going to look here at mixture distributions. For complex simulations, statisticians often use so-called mixture models. What is that? Well, let's look at a very simple example. Suppose that we have here a random variable x, and x is by definition equal to, well, pi times u1 plus 1 minus pi times u2, where u1 and u2 are also random variables, and they're going to be independent from each other. In addition to that, this pi that we've over here is in between 0 and 1. This is just a simple definition, but based on this, at least in the case that u1 and u2 are going to be, well, continuously distributed, then of course we can also look at the density of this x that we have over there. We can look at the density in relationship to the densities of u1 and u2. Well, then for you as econometricians, it should not be too difficult to, well, derive that the density of fx is simply equal to pi times the density of u1 plus 1 minus pi times the density of u2. The way you should do this, of course, is first of all, look at the distribution function and then take the first order derivative in order to get this density function over here. For example, if u1 and u2 are going to be one-dimensionally normally distributed with means equal to mu1 and mu2 and a common variance equal to sigma squared, well, then we're going to get this density function that we've over here, which is, of course, very nice to plot. Here we have on the x-axis, we have the different values of x. We had the previous slide. And on the y-axis, we have this density function for a particular case of that density function that we had the previous slide. Mu1 is equal to 0, mu2 is equal to 2, and sigma is equal to, well, it is equal to 0.5, and pi is going to be equal to 0.3. So then we are going to get this density function that we've over here. It's immediately clear that this is a non-standard density function because of the fact that it is going to be by model. We have a mode over here and we have a mode over there. And that is actually quite standard in, say, mixture models. Mixture models usually have densities that are multi-model. In this case, we have two different modes over here. And in this case, you should realize that it's, of course, not that surprising that they are at 0 and 2, because of the fact that not by complete coincidence, these are exactly equal to the means, because we do know that, well, apart from the fact that mu1 and mu2 are the means of a normal distribution, they're also the modes. So there we have a mode over here at 0, and we have another mode here at 2. Another thing which is interesting to see is that the first mode is smaller than the second mode, but that's of course because of the fact we have this pi equal to 0.3. But we can now go on to the general case. Suppose now that we have a situation in which we have a p-dimensional mixture distribution. The dimension is now, of course, with respect to this ui's that we have over here, and we have it of k different random variables where the ui's are going to be independent. Then we can define our mixture model x, or our mixture random variable x, as being simply the sum with respect to these pi i's multiplied with ui, where the sum of the pi i's must be exactly equal to 1. Well, then the density function, I don't think that that's so difficult to understand. The density function fx is then simply going to be equal to this sum that we have over here. But we will use, in my computer simulation, we will use mixture distributions, but we should realize that the idea behind mixture distributions is very intuitive in economics. We should realize that in many examples that we have in economics, for example, labor economics, it is typically the case that we do not observe everything with respect to a particular individual. So, for example, in labor economics, we do, of course, know the education level of a particular individual. We might know the gender of the individual, might know the race of the individual, maybe the age of a particular individual, but there are things we usually are not able to observe. And these are particularly the talents of individuals, their communication talents, their, say, how smart they are and things like that. So these are talents that we usually do not observe. And it's very common that these things actually come into groups. So they have different individuals that are in different kind of groups with respect to these talents that we have over here. Well, that can be very nicely modeled with respect to a mixture model as we have it over here, because of the fact that then the different UIs are going to represent different kind of groups in our population. But we should realize that an example of the use of mixture distributions in econometrics, well, there are various of them, but one that you might already have seen before is in mixed proportional hazard rate models. Not for any reason, of course, that we have here mixed proportional hazard rate models. I'm pretty sure that Gerard van den Berg has looked at duration models, and hopefully he also has been talking about mixed proportional hazard rate models. He has been one of the main experts in mixed proportional hazard rate models for a very long period of time. And well, there you actually also see that we are going to use a mixture distribution in order to look at the hazard rates. I would like now to go on with the example that we are going to look at. Remember that we have been looking at an example of computer simulation for quite a while. However, unfortunately, we cannot use that computer simulation anymore because of the fact that that computer simulation was with respect to the continuous case. And now what we're going to do is that we're going to look at classification. That means that we have to look at the new, say, computer simulation. Well, the computer simulation I'm going to use over here actually comes from a book by Hastie and others. Well, it must be somewhere at Nestor listed that we have also, we sometimes are using this book as well, or you could at least look at that book. It is not really an obligatory book to read for this particular course, but well, it is actually quite a nice book. And there you have actually this example that I'm going to use here over here as well. What we're going to do is that we're going to assume that there are two classes. I'm going to label them here as red and blue. Of course, that might be a little bit boring, but we will see that we're going to have very fancy pictures. But you can think of, for example, if you would like to have a little bit more of an example, red as being somebody who, for example, is going to get a heart attack in the next 10 years, and blue as being somebody who doesn't get a heart attack. Or we could think of red as being somebody who is not credit worthy, and blue as being somebody who is going to be credit worthy. In addition to these two classes that we have over here, we're also going to use P, the feature set, as being two different features. So we're going to have that X is going to be two-dimensional, going to have two different features, X1 and X2, and the realizations are going to be X1 and X2 that we have over here, little x1 and little x2. Now what we're going to assume is that these x's are going to come from a mixture of normals and from the two different classes that we have over here. But of course, the mixture distributions are going to be different. If these mixture distributions would have been exactly the same for red and blue, well, then we cannot do that much with respect to classification. Then the x's are not going to be not going to give us any information about how to classify the reds and the blues, but we are going to allow for the fact that the reds and the blues are going to have different kind of x's in the sense that their mixture distributions are going to be different. What that means is that we are going to assume that, well, the means that we have with respect to this mixture distribution are also going to be sampled. I'm going to say more about that at the next slide. And we are going to have common variances that are always going to be equal to 1/5. That means in the notation that we had in the previous slide, that P is going to be equal to 2, because of the fact that we have two different features. K now is going to be equal to 10. So we are going to have 10 different groups in terms of the UIs that we had in the previous slide. And we are going to assume that the probabilities are for all the groups exactly the same. And they're going to be exactly equal to 1/10. And then we are going to introduce a sample size of red and blue that is going to be equal to 100. Well, this is maybe a little bit different from what we typically do in computer simulations. What we typically do in computer simulations is that we're going to, sample the x's, and then based on the x's and based on the model that we have, we're going to decide whether somebody is going to have a particular outcome. That's also what we have done with respect to the previous computer simulation. But here we actually do the other way around. We, first of all, are simply going to say that we have 100 observations that are going to be red and 100 observations that are going to be blue. And then based on this, we are going to simply, get our axes. We are going to sample our axes. Well, based on this whole model that we have over here, and actually the means that I'm going to show you at the next slide, you can actually calculate the real decision boundary numerically. And the lowest possible risk that we in the end are going to get is a little bit below 19%. Again, this is going to be important because of the fact that at the moment we're going to look at applications, we do know that the, say, lowest possible risk that we can ever get for an application cannot be lower than this 0.1856 that we have over here. Also, this I actually have been calculating based on numerical, well, I actually have done numerical simulation in this case. So that means that, well, even if in the case that we're going to get the best predictor, that means that in 18.5 or actually 18.6% of the cases, we're going to have a misclassification. Well, this thing I still promise you to show you. These are the different means with respect to the mixture distribution. We already have seen that we have 10 different classes for both blue and red. And for both blue and red, we of course are going to have different means. So we have means of x1 for blue and means of x2 for blue. And the same we actually have for red. And then what I have done is that I actually have sampled these, say, means that we have over here, actually also from normal distributions, but I, well, even don't know myself anymore exactly how I actually have done that, but the distributions are not exactly identical. And as I remember, well, the distributions for x1 or the means of x1 for blue were a little bit higher, or at least the mean of those means was a little bit higher than for red. That's actually what you can see as well, but because in most of the cases, mu x1 is a little higher than mu x1 for reds. And we have done exactly the same the other way around with respect to blue. Well, it's actually not that important here, but the most important thing to realize is that what we have over here are different means. And then what we can do is that we can sample actually x1s and x2s for both blue and red. And that's what I've done in this slide that we've over here. So here on the x-axis, we have the different values of x1, and on the y-axis, we have the different values of x2. And as I already said, now what we simply do is that we're going to sample 100, say, observations for blue and 100 observations for red. What does that mean? Well, that means that first of all, I'm going to start with blue with respect to the very first observation. And then what I do is actually nothing else as the following. First of all, I'm going to, well, sample in which group that particular individual is. So suppose that that's going to be group number 4. Well, then it's going to be very simple. Then independently, because of the fact that I'm going to assume that x1 and x2 are independent from each other, but normally distributed, I'm going to, well, sample from a normal distribution with this mean for x1 and this one for x2, and variance is being equal to 1/5. I'm going to draw an x1 and independently an x2. And then I get a value that, for example, is equal to this observation that we have over here. And then I do that 100 times. I get them for blue, and I can do exactly the same thing at the moment that I want to have the 100 reds that we have over here. I can do a little bit more in this picture, and that is that, as I already said, we can numerically calculate the decision boundary that I have, well, calculated over here. Well, what I can do in general is that I can, for any x1 and x2 combination, I can calculate the probabilities that we have a y equal to red or a y equal to blue. That we can do using, in this case, another time Bayes rule. And then based on that, I'm not going to say exactly how we are going to do that. It's not that difficult actually. But then based on that, we do know which x1 and x2 combinations are going to have a higher probability for red and which combinations are going to be a higher probability for blue. But of course, there are also situations in which the probability of red and the probability of blue is exactly identical. And that can be calculated numerically, and that is this decision boundary that we have over here. This is the theoretical decision boundary that we have over here. These are all those combinations of x1 and x2. for which the probabilities red and blue are exactly identical to each other. Well, and then what we can do is that we can make this nice picture that we have over here because of the fact that this blue area are all those x1 and x2 combinations for which the probability of having a blue, conditional of course on the axis, is higher than the probability that we have a red. And in the red areas that we have over here, that is this area that we have over here, as well as that area that we have over there, well, these are all the combinations of x1 and x2 for which the probability that we have a red is higher than blue. Well, what does this mean? Well, that actually means that based on the theory that we have already seen before, that actually this blue and red, it's not just looking very nice, but it's also going to give us the best predictor. So that means that at the moment that I will have an observation that is in this blue area over here, well, with respect to this training set, but more important, of course, for any, say, future x1 and x2 that I'm going to receive, then what I need to do is that I have to predict, if it's in this blue area, then I have to predict it to be blue. That would be the best case situation. Then I'm going to do the best prediction. And then in addition to that, at the moment that I'm going to have an x1, x2 combination that is in the red area, well, then you should realize that I should always make a prediction that is going to be red. Well, again, we see that, as we have seen also in the other computer simulation, that even though this is the best predictor, that doesn't mean that we always are going to be correct, because we do see that there are some red dots over here that are actually in the blue area. That would imply that, for example, at the moment I'm going to have this red dot over here and somewhere in the future, then what I'm going to do is that I'm going to predict it to be blue. However, at least in this training sample that we have over here, it was actually a red outcome. And that means, of course, that even though we have the best predictor, we do sometimes make mistakes. And the reason why we actually don't, in this case, say like, well, maybe we could have been even better off by, say, predicting this area to be red, is because of the fact that you should realize that even though we have here a red outcome, the probability in this outcome that we have over here, that we are going to have a blue outcome, is always going to be higher than the probability that we're going to have a red outcome. That doesn't mean, of course, that you cannot have a red outcome, because even in the case that there's only, say, 25% probability here that you have a red outcome, you can still have a red outcome here, of course. So therefore, in this particular case, it is better for any kind of prediction to actually predict this thing to be blue for now on into the future, for any kind of prediction that we're going to have. And that brings me back to the thing that I already said before, and that is that there is a difference between having a good model fit and having a good predictor. For having a better model fit, indeed, it would have been better if I, for example, would have said that this would have been a, say, red area over here, at least here around this red dot that we have over here, because of the fact that then I would have made a better prediction in a sense of this model, the data, the training data that we have over here. But that's not what we want to do with respect to machine learning. We don't want to get a good fit of the training data. We want to get a good prediction. And you can actually show that based on the theory that you have so far, that this is going to be our best predictor. Okay, I would like to go on, and I would like to go on with the first algorithm that we're going to look at, and that is a famous one because of the fact that that's simply regression. In order to introduce regression, the best thing to do is that we're going to look back at the example that we have been introducing at the previous slides, and that implies that we're going to introduce a dummy variable, yi, and let's make this yi as follows. Yi is going to be equal to 1 in the case that we have a blue observation, and yi is going to be equal to 0 otherwise. Then in that case, we can run the following regression. We can run a regression of y on x1 and x2. So there we're going to get y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus u. We're going to make the assumption that u is going to be uncorrelated with x1 and x2. Well, then we already know for a long time that at the moment we're going to look at the mean of y conditional x1 equal to x1 and x2 equal to x2 is then going to be equal to beta 0 plus beta 1 x1 plus beta 2 x2. Well, a thing that you might already know from linear probability models is that we can also, in this particular case, so only in this particular case, we can also rewrite the mean of y conditional x1 equal to x1 and x2 equal to x2 to the following. We should take into account that y can only take two outcomes. So therefore the mean is always equal to, well, the first outcome, which is equal to 0, multiplied by the probability of 0, plus the second outcome, which is equal to 1, multiplied by the probability of 1. Well, based on this, it is immediately clear that this first part is going to cancel out, and also this 1 we don't have to write down. So therefore we immediately are going to get that we are going to have that also the mean of y conditional x1 equal to x1 and x2 equal to x2 is equal to the probability that y is equal to 1, conditional on x1 is equal to x1 and x2 is equal to x2. We can combine these two equations to derive that the probability that y is equal to 1, conditional on the x's, is equal to beta 0 plus beta 1 x1 plus beta 2 x2. So that implies that in this particular case we can get the probabilities from this linear probability model by simply running a regression of y on x1 and x2. Then we're going to get estimators of beta 0, beta 1 and beta 2, and then we get this probability over here. Well, likewise, we can also get the probability of y equal to 0 conditional on x1 and x2. Well, that's of course equal to the probability of 1 minus the probability that we're going to have a 1. And then what we can do is that we can then realize that we already know that from the previous slide. So then we get this relationship that we've over here. Therefore, if we would like to determine when we should actually go for a prediction, in this case, of blue, so that means that we're going to look at this x1, this calligraphic x1 that we have over here. Well, we should, classify a blue or predict a blue in the case that the probability that y is equal to 1 is larger than the probability y equals 0. Well, then what we can do is that we can simply substitute the things that we have at the previous slide here at the left hand side and this thing that we have over here at the right hand side. If we're going to do that, then we are going to get this combination that we can rewrite a bit. We can bring all these terms to the left hand side. They're exactly identical to these terms over here, so therefore we simply get 2 times all these terms over here must be larger than 1. Then we can divide the left and the right hand side by 2 in order to get this thing over here. And then the next thing that I can do is that I can bring these 2 terms to the other side and then divide by beta 2 in order to get this relationship that over here. That means, of course, that at least theoretically, if we know the beta 0, beta 1 and beta 2, well, then we should always go for a blue prediction based on the assumptions that we have made. Then we should always go for a blue prediction at the moment that x2 is larger to this thing that we have here at the right hand side. And that means, of course, that delta x is our decision boundary, and that is now going to be simply all those combinations of x1 and x2 that are going to be equal to this relationship over here. Well, we should realize that, of course, we do not know beta 0, beta 1 and beta 2, but as I already said, we can actually estimate them by running a linear probability model as explained in the previous slide. Get the beta 0, beta 1 and beta 2 hat, and then you should realize that this in general is nothing else as a linear line of x2, well, in terms of this x1 that we have over here. If we're going to do that for our particular case, then again we have the x1s at the x-axis and the x2s at the y-axis, then we're going to get this line that we have over here based on the estimation of beta 0, beta 1 and beta 2 based on this training sample that we have over here. And that implies that in this particular case, at the moment that we are in this blue area that we have over here, well, then the probability of having a blue according to our model is going to be higher than the probability of having a red. So therefore we then should make a prediction of blue. And at the moment that we are going to be in this area, in this red area that we have over here, well, then we are going to see that the probability of having a red is higher than having a blue. And that means, of course, that it's better to make a prediction here equal to red. So that is what we are going to get right now. The question arises, is this actually a very good prediction? Well, the answer to that is obviously no. And that's not because of the fact that the fit in this case is not so great, but it's essentially because of the fact that we do already know that our optimal decision boundary, the real decision boundary that we should have in the optimal case, is equal to this dashed line that we have over here. I have repeated it over here, and we do immediately see that there's quite a big difference between our decision boundary that we have been estimating and this, say, decision boundary that we have over here. And then we immediately see, of course, that based on the, say, predictions that we must have made, well, this would have been a blue area, this would have been red, and this would have been red as well in that particular case. Then we do see that here we make blue predictions, but they should have been red. That's actually here as well. And in this whole area that we have over here, we are going to see that we are going to make red predictions, but officially they should have been blue. So that means, of course, that based on this, we are not making that great predictions. That is, of course, based on the fact that we have assumed here that our decision boundary is going to be a linear line. That is what we do with respect to regression, and we should realize that that is definitely not the case with respect to our real decision boundary that we actually get from our best predictor. It's immediately clear you don't need to know that much about mathematics to see that this is actually not at all linear. The question, of course, arises, could it sometimes be the case that the real decision boundary is going to be a linear line? The answer to that is yes, but that's only going to be in the case that the underlying distributions of, say, x1 and x2 with respect to the red group and the blue group that we have over here, so the red class and the blue class that we have over here, they must be unimodal. So they are allowed to be different from each other, but these, say, distributions, they should be unimodal. Then in that particular situation, the decision boundary is really going to be a straight line, and that is a situation in which regression analysis, standard regression analysis, is going to work very, very well. But we should realize that in all other cases, regression analysis, the performance of regression analysis is not going to be so great. And you should realize that having unimodal distributions is, of course, a very, very restrictive assumption. So the question arises, can we do something about that? Well, I have already discussed that. One thing that we could do is that instead of just including x1 and x2, we could try to estimate a so-called polynomial. What we can do is that we can start with a polynomial of the second order. That means that apart from including x1 and x2, we're also going to include x1 squared, x2 squared, and x1 multiplied by x2. Then we actually are going to get this picture that we have over here. And it's immediately clear that this picture already is much better than the picture that we had before. Now we still see, of course, that our decision boundary that looks like now more like an egg or something like that, well, that actually is going to, well, be different from the best decision boundary that we can ever have. And we also see that sometimes we make the wrong predictions in the sense of comparing it with the, say, optimal predictor, for example, over here and over there, but it's already much better than what we have seen before. Of course, we don't have to stop with a polynomial of the order 2. What we could have done is that we can even look at a polynomial of the order 3. At the moment that we're going to do that, then we're actually going to get this thing that we have over here. Well, it's a little bit difficult to see whether this is so much better than what we had before with respect to a polynomial of the order 2. One thing which is always a bit funny to see in a sense, at the moment that we're going to look at higher orders, is that we get these kind of strange things over here. Here we are going to see that if we're far enough from the blue area, then at the particular moment in time we get blue predictions again. Well, this is completely related to the parametric form that we have over here, and you should realize that that usually is going to happen more and more at the moment that we're going to make the polynomial of a higher order. Well, as I already said, it's a little bit difficult to see whether this is better than what we had before, but what we can do is that we can even look at higher order polynomials. For example, here we have a polynomial of the order 4, and we can even look at a polynomial of the order 5, then we get this picture that we've over here. Well, these two pictures, in my opinion, now look actually quite good, so probably the performance is going to be better. But what we, of course, have to do in order to make a decision with respect to all these models that we have over here is that we have to do either looking at a validation sample, or we have to look at cross-validation in order to make a choice with respect to all these different models, as we always have. Well, what we can even say is that we might here use either rich or the lasso in order to actually do regularization with respect to the higher order terms. Well, I would like to go on with respect to regression, and what I would like to discuss right now is to how can we actually extend regression for the situation in which C is going to be larger than 2. Well, that's actually not that difficult in regression, but then we should realize that our outcome variable then is no longer going to be a dummy variable, but our outcome variable is then going to be actually a factor. So y then in that particular situation is going to be a factor, where, for example, the very first element in that factor is going to be a dummy variable, or whether we are going to be in the first class, whether this y over here is going to be, well, our outcome variable is going to be equal to 0 or not. And then the second element is going to be the situation in which we are going to be in the second class, so whether the original yi that we had is going to be equal to 1 or not. Well, then we are going to get a full factor, of course, and then our observed y that we have over here is going to be a full matrix. But still what we can do is that we can simply do now, in this case, multivariate ordinary squares. So we're simply going to, well, do this matrix multiplication, and then this b hat that we're then going to have is no longer a factor of coefficients, but it's going to be a p by c matrix, p being the number of features that we have, and c the number of classes that we are going to have. But the idea is exactly the same as what we had before. What we can do is that we can predict the probabilities, of course, based on multiplying an x that we are going to have for a particular, say, observation, and we're going to multiply that x with respect to this beta hat that we have over here. This will actually give us a factor of probabilities, and then what we're going to do is that we're going to predict that particular class for which the probability is going to be highest. I would like to now go on with the next topic, and that's the topic of nearest neighbors. We have already looked at nearest neighbors before, but we have to, say, adapt the method of nearest neighbors a little bit at the moment that we're going to look at classification. But the idea is still the same. What we're going to do is that we're going to look at all those observations, k observations, that are nearest in terms of the axis. But then what we can do is that we cannot do exactly the same as in the continuous variable case, that we're going to take the average over all those k nearest neighbors. But now what we're going to do is that we're going to sum, say, the outcomes, and we are going to, in a sense, count the number of times that we have an outcome of a particular class. And then we are going to predict that particular class that is going to be most frequent, for which we have among these k observations that we have over here that occur the most. So suppose that we are going to simply look at blue and red, and we have, say, 15k here is going to be equal to 15. Well, then what we're going to do is that we're going to, say, predict blue at the moment that among these k observations that we have over here, well, the observations that we have, there are 8 or more observations that are going to be blue. And at the moment that we have 8 or more observations that are going to be red, then at that moment in time, of course, we're going to make a prediction that is going to be red. Well, that works in our case as follows. Here we have nearest neighbors estimation for k equal to 15. And then what we're going to get is well, this now is going to be our decision boundary. Looks not as smooth as what we had before, but one thing that we can immediately say is that now, of course, we are going to make a prediction equal to blue. At the moment that we're in this blue area, and we're going to make a prediction which is going to be red in this red area that we have over here. And actually you can immediately see that here at least nearest neighbors does actually quite well, because of the fact that we do not see a large difference between, say, this optimal decision boundary that we have over here and the decision boundary that we now have been estimating based on nearest neighbors, with k being equal to 15. Of course, it doesn't look that smooth in a sense, but apart from that, generally we are actually quite close by. Of course, this depends a lot on the k that we're going to use. For example, if I would not have used k equal to 15, but for example k equal to 50, well then I would have not had such a nice representation over here. This actually looks, well, surprisingly close to the, well, standard linear regression model as we have looked at before. And well, what we could have done is, of course, choosing k equal to 50, but we could have also have chosen a k which was really, really small. Then we get something like this. Well, you should realize that this actually is also not such a great predictor. And the reason behind that is because of the fact that even though the fit is going to be better, we do see all these strange areas in which we are going to have reds in this blue area that we have over here. And that's only done because of the fact that we would like to, in a sense, overfit the training sample. And that's a problem that we have in general with respect to nearest neighbors, that at the moment that k becomes small, the situation would have been even more, well, worse at the moment, that k would have been equal to 1, because of the fact that then we would have drawn all kinds of small red areas around all these points that we have over here and having a perfect fit. What we should realize is that for k's being small, nearest neighbors has the tendency to overfit, in fact, the training sample. And that means, of course, as usual, that what we need to do in order to get the best k is what we have to do is cross validation. Okay, I would like to go on with the next topic, and that's the topic of linear discriminant analysis, or generally speaking, discriminant analysis. The idea behind discriminant analysis comes from Bayes' rule. We do already know that Bayes' rule says that the probability of y conditional on x can be written as the probability of x conditional on y multiplied by the probability of y divided by the probability of x. Well, now it depends a bit on whether x is going to be continuous or not, but let's assume that x is going to be a continuous set of features. Well, then at that moment in time, what we need to do is that we have to write this as density. So we are going to have a density over here and a density that we have over there. Now we should realize that in linear discriminant analysis, we are usually not that much interested in the probabilities themselves. We are usually much more interested in the relative probability. Say the probability that y is equal to I relative to the probability that, for example, y is equal to j, where I is of course not equal to j. Now you should realize that that implies that we don't really have to use here these probabilities over here that we have at the right hand side. And the reason behind that is because of the fact that we typically, or in all cases, are going to divide here by this constant that we have over there. This is constant for any probability that we have here at the left hand side. So therefore, what we can do is that we can also write it in another way. That is that we are going to have here that the probability of y is equal to I conditional on x equal to x is going to be proportional to this, well, flipped alpha that we have over here means actually proportional to, and it is going to be proportional to the, say, density of x conditional on y multiplied by the probability that y is equal to I. And this last probability, well, I'm going to rewrite it a bit because of the fact that I'm going to define this probabilities being equal to this pi I that we have over here. This is usually called the prior probability. So then we are going to get this thing that we have over here. It's the prior probability for class I, well, what you can say is that prior probabilities are actually nothing else as probabilities that we have at the moment that we do not know anything about a particular observation. Take into account that what we usually do at the moment that we're going to do classifications, or at the moment that we're going to make predictions, then what we typically do is that we take the x value of a particular observation into account. Well, suppose that we're not going to do that, for example, because of the fact we do not know what the x value is, then the question of course arises, what is then the likelihood that we have a probability that y is going to be in this class I that we have over here? Well, that's of course this prior probability that we have over here. Well, very generally speaking, and this is the central idea behind Bayesian statistics, what we can say is that the left-hand side, according to Bayesians, is usually called the posterior that we have over here. And what Bayesians usually say is that posteriors are always equal to, well, the prior that we have over here, multiplied by this thing that we have over here, which is typically called the likelihood. Well, that's actually not that important for us right now. We are looking here at linear discriminant analysis and not at Bayesian statistics, but it's going to be somewhat helpful because of the fact that we should realize what is this thing that we have over here. It's the density of x, well, conditional on a particular class that we have over here. Well, now suppose that we have a particular situation in which we do know that a particular class has a very high likelihood of having a particular value of the axis that we have over here. What does that mean? Well, that means, of course, that at the moment in time that we are going to see a particular individual observation that has this x that we have over here, that has an x that is quite affluent for a particular class, well, then you should realize that the likelihood that that particular observation belongs to that class is going to be high as well. Well, that's the whole idea behind linear discriminant analysis. Now what we could do is that we could make some parametric form assumption with respect to this density that we have over here, this conditional density that we have over here. Let's assume it to be normally distributed. Well, this is of course going to be a density with respect to, well, the features that we have, and the features are p-dimensional, so therefore this density that we have over here is going to be p-dimensional as well. And well, that means of course that well, what we are going to get then is that we are going to have a mean, which also is going to be p-dimensional, and we're going to have a covariance matrix which is going to be equal to p by p for every single class that we have. And that implies, of course, that we then can write our probabilities, these probabilities that we already had over there, well, as being proportional to the density. This is the density of a p-dimensional normal with respect to this x that we have over here, multiplied by this probabilities that we already had over there, these prior probabilities that we had already over there. Well, now consider the so-called log-odds ratio. The log-odds ratio between group I and group J is actually nothing else as the logarithm of the probability that y is equal to I, conditional on x equal to x, divided by the probability that y is equal to j, conditional on x equal to x. A nice thing is that there is a clear relationship to, well, what we are going to predict and in fact this log-odds ratio that we have over here. Because remember that we always are going to predict a particular outcome to be equal to I at the moment that the probabilities of y equal to I is always going to be larger than, well, the probability that y is equal to j for any I unequal to j. So therefore the probabilities of y equal to I should be always larger than any other probability that y actually can have. Well, we should realize that that of course means nothing else is that the log-odds ratio of this class I compared to any kind of class j that we have over here should be larger than 0. Because at the moment that this is going to hold, then of course this numerator divided by the denominator is always going to be larger than 1. And that means of course that the logarithm should be larger than 0. Well, more in particular, at the moment that we're going to look at a case that c is equal to 2, then we can even look at the decision boundary. For the decision boundary, at the moment that we only have two different outcomes, 0 and 1, well, for the decision boundary, we must have that this log odds ratio must be exactly equal to 0. That means, of course, nothing else as that based on the probabilities that we had in the previous slide, that we must have that this probability that y is equal to 1 must be equal to the probability that y is equal to 0. So therefore we must have this equality along the decision boundary that we have over here. Well, then what we can do is that we can then, well, first of all, rewrite this a bit. We can realize that these two things, of course, are going to cancel to each other. And then the next thing that I can do is that I can bring all these terms to the other side. And well, then I can take these two pi's that we have over here, I can take them together in order to get this relationship that we have over here. And now the idea, of course, is that, well, along the decision boundary that we have over here, in order to calculate the decision boundary, at least numerically, what we need to do is that we have to look at all those combinations of x that we have over here that are going to be exactly equal to 0. So we have to solve this equation that we have over here in order to get this decision boundary, and based on that, we can know when the probability that y is equal to 1 is going to be larger than the probability that y is equal to 0. Well, this is still quite difficult, so therefore what we might want to do is that we are going to simplify this a little bit. One thing that we can do is that we can assume that even though the mu's that we have over here are still different, that the sigmas, the covariance matrices, for the two groups are exactly the same. If you're going to do that, then we are going to get this equation that we have over here. Well, this is of course a simplifying equation, and the first thing that we immediately see then is that these two things that we have over here, they're going to cancel each other. But we can do more things. We should realize that this term that we have over here, we can get rid of the parentheses, and this term over here is actually nothing else as a so-called quadratic form. That means, of course, that we first of all are going to have x transpose multiplied by the inverse of sigma multiplied by x. We're going to get minus 2 times mu1 transpose multiplied by the inverse of sigma multiplied by this x that we have over here. And then finally we're going to get, well, mu1 transposed multiplied by the inverse of sigma that we have over here multiplied by this mu1 that we have over there. So therefore we get all these terms over here, but we still have to multiply it by minus a half. So therefore, in the end, this results in these 3 terms that we have over here. Well, in exactly the same way, what we can do is that we can rewrite these terms that we have over here. So then what we're going to get in the end are all these terms over here. Well, then it's immediately clear that this term is going to, well, cancel with that term that we have over there. So therefore, what we're going to get is simply this thing over here. And then what we can finally do is that we should realize that we have here xt times sigma minus 1 times mu1. And here we actually also have x transpose times sigma minus 1 times mu0. So then what we can do is that we can get parentheses, we can take this outside of parentheses and then multiply it by mu1 minus mu0. Well, if you're going to look at this thing that we have over here, then you should recognize that this is actually nothing else as a linear system of equations. So therefore, it's going to be now very easy to find, in fact, the x's that are going to be on this particular decision boundary that we have over here. More in particular, what you can say is that this now is going to be a linear line, so to speak, with respect to the different axes. In this case, the, say, axis that we are going to have in our analysis. Well, at the moment that we only have a situation in which c is equal to 2, well, then you can actually show that what we're going to get over here is something which is exactly equal to, well, standard linear regression analysis. But we are not there yet. The problem is that we still have to calculate this mu0 that we have over here and the sigma that we have over there, as well as this pi's that we have over there. Well, take into account that we have a parametric model, and that means, of course, that we can estimate this with respect to maximum likelihood. So therefore, first of all, we can estimate this with respect to maximum likelihood, where pi hat then, well, very generally, then is going to be equal to ni over n. This actually also holds even in the case that c is going to be larger than 2, where ni is here going to be the number of observations in class I. Then mu I hat is simply going to be then the sample average with respect to the axis in the class I that we've over there. Well, and with respect to sigma, well, sigma is going to be a little bit more difficult. What we can do here as well is that we can simply look at the, say, estimated sample, well, covariance matrix for a particular class. Say, for example, this class I that we have over here. Then we get this estimator that we have over here. However, we should realize that, well, even though we can actually do that, all the sigmas are exactly identical, so therefore we can simply pick one of the different classes I that we've over here. But in order to make things more efficient, what we can do is that we can then, well, average with respect to all the classes that we have. Well, if we're going to do this, then what we're going to get is something which is called linear discriminant analysis. And I already said that at the moment that the number of classes that we have is equal to 2. Then our result that we're going to get is exactly the same as with respect to linear regression. So therefore, this picture is exactly identical to what we had with respect to linear regression analysis. So therefore, I don't have to say too much about this picture anymore, but I would like to go on with the extension with respect to that. We already know that, well, linear regression doesn't work so fine. So therefore, the question arises, what could we do? Well, one of the things that we could do is that we could realize that the assumption that we have made so far with respect to equal variances, well, that was of course very restrictive. Maybe we can just simply drop that particular assumption. Well, then we are actually back in this equation that we have already seen before. And then what we need to do is numerically try to solve these, say, x's with respect to that decision boundary that we've over there. Well, that of course can be done, numerically at least. Well, actually, at the moment that we're going to then look at the sigma i's, then in this case we have to estimate the sigma i's, in this case sigma 0 and sigma 1. Well, the estimators of that is going to be a little bit simpler because of the fact that then it's simply only going to be the sample, well, the sample variance covariance matrices with respect to the different classes. Well, if we're going to do that, then we no longer have linear discriminant analysis, but then what we have something which we call quadratic discriminant analysis, or sometimes called QDA. If we are going to do that, then in our particular case, what we then are going to get is this picture that we have over here. Well, it is immediately clear that this actually looks much better than what we had before with respect to LDA, and take into account that here I haven't included any additional terms yet. I haven't included any additional terms with respect to x1 and x2, so x1 squared or x2 squared, as we have done with respect to regression analysis. That you can of course always do, but you should realize that QDA actually doesn't include any of these additional terms, but by itself it is already, say, non-linear, and therefore we get this thing that we have over here. I would like to go on with the final algorithm that we're going to discuss today, and that's logistic regression. Logistic regression makes one main assumption, and that is that the log odds ratio is going to be a linear regression line. So that means that the log odds ratio of any of our classes, I being equal to 1 till c minus 1, is with respect to the first class, so the case in which y is equal to 0, that log odds ratio can be written as a linear line beta I0 plus x times beta I1. That's the main assumption that is going to be made by logistic regression. Well, if we're going to make this assumption, then we can immediately rewrite this a bit. First of all, we can take exponentials from the left and the right hand side, and then we get this relationship that we have over here. Then I can multiply the left and the right hand side by the denominator that we have over here, the probability y is equal to 0, conditional on x equal to x, in order to get this relationship that we have over here. And then what I can do next is that I can sum over all the different classes, well, at least from 1 till c minus 1, so all the classes, apart of course from the first class. Then, well, at the left hand side I'm going to get this thing over here, based of course on what we have over there. And then I also have to sum over all the classes at the right hand side. Then I get this thing that we have over here. Well, now we should realize that summing over all the classes apart from the first class, so the class that we label by 0, well, that will of course be simply equal to 1 minus the probability that y is equal to 0. So we can also write it like this. Then what I can do is that I can bring this to the other side and take it together with this term that we have over here in order to get this over here. Then finally, if I'm going to divide the left and the right hand side by this thing that we have over here, then we're going to get this probability over here. So now we can immediately calculate the probability y is equal to 0, conditional on x equal to x. That was still here, so if I'm going to substitute this into there, then I'm going to get that, well, every other probability than I equal to 0 can be simply written as this relationship that we have over here. Well, if c would have been equal to 2, and then we would have calculated this thing over here, then we actually get the famous logit model. So that means nothing else is that in that particular case, well, we can directly estimate the beta coefficients that we have over here by maximum likelihood. We can even do that with Stata in this case. Stata can directly calculate us these beta coefficients that we have over here, and then we can even predict the probabilities, because of the fact that actually in Stata is also very simple. We just write down predict, and then we get these probabilities. In this case, well, if c is equal to 2, we get the probabilities that y is equal to 1, these things that we get over here. And of course, very easily we can also get the probabilities or the predicted probabilities that y is equal to 0. And then, of course, if these predictions are going to be equal or higher than a half, or strictly higher than a half, then in that particular situation we're going to choose or predict class 1. And at the moment that these estimated probabilities are going to be smaller than a half, then it's better to predict class 0. At the moment that c becomes larger than 2, well, then we no longer have a standard logit model, but then what we're going to get is a so-called multinomial logit model. Also, that can be very easily estimated, again, for example, using Stata. And then what we're going to do is then we are going to choose that particular class that is going to have the highest estimated probability. Well, as usual, in order to get the best model, what we should do is that we should do a cross-validation with respect to what we are going to include in this x that we have over here. So which features are we going to include with respect to this x that we have over here, including, of course, the higher order terms. So apart from the features themselves, we're also going to ask ourselves the question, which higher order terms should be included? Well, that we should always do based on validation. So either we're going to use a validation sample and calculate it based on the validation risk, or we're going to use the cross-validation risk at the moment that we're going to do cross-validation. Well, then finally, we could even do something that, well, we have already dealt with before, and that is that we can look at regularization. What we can do is that we can do maximum likelihood, but then what we're going to do is that we can subtract from that, for example, L1 norm, multiplied, of course, by a regularization parameter lab that we have over here. So that looks a lot like Lasso in this case. If we would have had an L2 norm, then in that particular situation, we would have had something that is very like rich regression. Well, at the moment that we're going to do this with respect to our particular example, then we're going to get this thing that we have over here. Well, logistic regression is almost identical to standard regression analysis. We don't get exactly the same say, line over here with respect to logistic regression. But in general, the results that we're going to obtain with respect to logistic regression are not that different from standard regression analysis. Well, that brings me to one of the final slides that we have over here, and that is that we now can compare the different methods that we have looked at so far. We have looked at linear regression, we have looked at quadratic regression. Well, we actually have looked at higher order terms with respect to our regression analysis, but they are not listed over here. We have been looking at nearest neighbors, LDA, QDA, and finally we also have been looking at logistic regression. Well, we do see that linear regression, LDA, and logistic regression actually don't perform so well, most likely because of the fact that they assume a linear line, whereas we do of course know that our, say, setup is in such a way that we should not have a linear decision boundary. Well, we do see that the other methods that do not make these assumptions actually perform much better. Quadratic regression already performs much better, but of course, generally we can say that QDA as well as nearest neighbors are the best performers. Actually, nearest neighbors already gets quite close to the lowest level that we could ever actually get, and that was something around 0.1865, 56 actually. So therefore, actually nearest neighbors here performs already very, very well. However, we haven't done any cross-validation yet. What I have done so far is just run all these kind of things without asking ourselves the question whether we could do some additional cross-validation. Well, that is this next slide. What we're going to do is that we, for regression, logistic regression, LDA and QDA, we're going to use higher order polynomials. For nearest neighbors, we're going to choose K. And for rich and lesser, we're going to use the lambda that we've over here. Well, now we see a completely different picture. Now we actually see that there are not that many differences anymore with respect to the different methods. Actually, even simple regression analysis already performs actually quite well, and we still see, of course, that LDA is exactly the same. Logistic regression even performs a little bit better, but of course, still some of the, say, more difficult methods are going to perform even better. We are going to see that QDA performs better, and nearest neighbors actually even performs a little bit better, but only slightly better than what we had in the previous slide. Finally, rich and lasso, of course, also perform better than regression, where again we have that rich performs a little bit better than the lasso.